Alright, so let's take a look at our last example here. It says use the areas of the region bounded by two graphs to solve real-life problems. So this is a problem on energy consumption. It says the projected fuel cost, C, in millions of dollars per year for a trucking company from 2020 to 2032 is given by C1 equals 2.21 T plus 5.6. Again here, T is between 20 and 32, so it seemed to me like T is the years past 2000. It says where T equals 20 corresponds to 2020. After purchasing more efficient truck engines, the company expects the fuel cost to follow the following models. C2 equals 2.04 T plus 4.7 for 20 less than or equal to T less than or equal to 32. How much money will the company save on the more efficient engines? So what's the idea? We want to find the total cost over the years for the first one, the total cost over the years for the second one, and then subtract the two of them. If you notice, I can tell right away just by looking at these that this first function is going to be the top function, the second function is going to be the bottom function. Why can I tell that? Well, there's multiple reasons that I can tell that. The first reason being, number one, they say it's less expensive, so that cost should be lower. Number two, I could just start plugging in numbers, any number between 20 and 32, and figure out which one is the top function, which one's higher, which would be the top function, which would be C1, which one's lower, which would be the bottom function, which would be C2. So if I want to find the total cost, what I'm going to be doing is integrating that cost function. But here's the beautiful thing. I want to know the total cost for the top function minus the bottom function. So what I could do is the integral from 20 to 32 of that top function, which was the 2.21 T plus 5.6, minus the bottom function, which was the 2.042 T plus 4.7. I can integrate the difference of those two with respect to T, and that's going to give me exactly what I need here. So let's do some cleaning up. This is going to be the integral from 20 to 32. Go ahead and in your calculators do 2.21 minus 2.04. I'm getting 0.17 T, and then do 5.6 minus 4.7. I'm getting plus 0.9, and this is with respect to T. So now I can go ahead and integrate and then evaluate it at the limits of integration. So this should be 0.17. The integral of T is T squared. This would be over 2 plus the integral of a constant, which is 0.9, would be 0.9 T. But then I need to evaluate this at my limits of integration, which are 20 to 32. I always start by plugging in my upper limit of integration. So I have 0.17 divided by 2 times 32 squared plus 0.09 times 32. I have now plugged in my upper limit of integration. Now I need to subtract off plugging in my lower limit of integration. So that'd be 0.17 divided by 2 times 20 squared plus 0.9 divided times 20. I plug those numbers in. Be very careful here. I'm going to go ahead and round to 2 decimal points. It doesn't say what to round to, so I'm going to round to 2 decimal points. I'm getting approximately 63.84, but let's figure out what the heck that means. It says the projected fuel costs in millions of dollars per year. So how much money is this company saving? They are saving, by buying these new trucks, approximately $63.84 million. $63.84 million in fuel costs between these new engines. So would this be an investment worth making for this company? Well, as long as these engines cost less than $63 million, they would be making they'd be saving money on fuel costs. As long as those engines cost less than the amount they're saving in fuel, this would be a good deal for the company to make.